Hello, my name is Alexei. Let me introduce you to my research related to electrochemical fabrication of bismuth telluride, bismuth superlattices for thermoelectric applications. Bismuth telluride is one of the best thermoelectric materials at room temperature, but the thermoelectric figure of merit, even of bismuth telluride, is insufficiently high for most thermoelectric applications on a large scale. The prospective way to improve significantly the figure of merit of the layered structure of bismuth telluride consists in the reduction of lattice thermal conductivity by introducing interlayers between bismuth 2 tellurium 3 quintuples. In this work, we have developed the electrochemical synthesis of the simplest superlattice structure based on bismuth telluride, bismuth 2 tellurium 3 bismuth superlattice with bismuth atomic bilayers. These superlattices are of interest as thermoelectric material in itself and can be also used as initial substance for preparation of more complex superlattice structures. Our electrochemical procedures and experimental evidence of the superlattice structures have been just published in the Journal of Power Sources. So the main goal of this presentation is a brief overview of the electrodeposition and the latest results of its optimization for fabrication of the superlattices in the form of compact, high-quality films. I will also present our results on the further electrochemical modifications of the electrochemically deposited superlattices. According to the phase diagram of bismuth-tellurium binary system, heterogeneous system is formed at high tellurium content, whereas high bismuth content favors formation of variety of stoichiometric compounds like bismuth 2 tellurium 3, bismuth 4 tellurium 3, bismuth 2 tellurium, and etc. The composition of these compounds can be described as a combination of two types of building blocks, a 5-layered bismuth 2 tellurium 3 quintuple and a 2-layered bismuth bilayer. In literature, structures formed by combination of these two types of building blocks are designated as infinitely adaptive structures. The infinitely adaptive series is not limited to stoichiometric compounds. In fact, any composition between the two lines of the phase diagram is possible. This slide shows cyclic voltammograms for the electrodeposition of bismuth telluride from the solutions of its precursors and the subsequent anodic oxidation of the electrodeposits. The film deposition is the reduction process, and it proceeds at negative potentials. Bismuth 2 tellurium 3 oxidation proceeds at more positive potentials. With increase in the concentration of bismuth cations in the electrolyte used for electrodeposition, an additional process is observed in the anodic scan. The potential corresponding to this process is intermediate between the oxidation of bulk bismuth telluride and metallic bismuth. This process corresponds to the selective oxidation of the interlayered bismuth in bismuth 2 tellurium 3 bismuth superlattices, and the thorough proof of this was presented in our article in the Journal of Power Sources. For the electrodeposition of the films of bismuth telluride and superlattice structures, we chose the pulsed electrodeposition mode with a square potential wave. Deposition potentials were determined from cyclic voltammograms. Here are the potential and current profiles in the pulse electrodeposition of the superlattice. The cathodic current is attributed to the film deposition. Anodic current prevents nucleation of bulk bismuth and controls bismuth interlayers. The composition of films determined with atomic absorption spectroscopy shows clear dependence on the electrolyte composition, and this provides efficient control of the relative number of the building blocks in the superlattices. X-ray diffraction patterns correspond to high degree of crystallinity of the synthesized bismuth tellurium films and show no peaks related to other phases. The position of peaks is slightly variable. We applied profile fitting to determine the corresponding variability of the lattice constants. What we expected to find out from the refinement? In literature, the compounds of this series are described with the so-called stacking model. The stacking model assumes no interaction between stacking blocks. Lattice constants, according to the stacking model, can be calculated using the following formulas. On the other hand, structure optimization with density functional theory has disclosed the interaction between the stacking blocks, manifested especially in the shrinking of C lattice parameter. Our experimental results fall in between those predicted by DFT and the stacking model, thus indicating the interaction between the building blocks of the superlattice. The refined lattice parameters were in the agreement with the microscopy data, as shown in this slide. One more evidence of bismuth bilayer formation was found from analysis of binding energies corresponding to 5D bismuth core levels in X-ray photoelectron spectroscopy. As we electrochemically obtained the superlattices in the potential region of metallic bismuth oxidation and below the potential of bismuth bilayer oxidation, the observed bismuth contribution in XPS was a convenient indicator of the interlayers. Returning to cyclic voltammetry, we see the anodic oxidation of bismuth bilayer proceeds well below the potential of bismuth telluride anodic oxidation, and this gave us the idea to selectively oxidize those bismuth bilayers, leaving the crystal structure distorted. We compared the effect of the anodic treatment at the potential of bismuth bilayer anodic oxidation at different bismuth content in the electrodeposited films. As this slide shows, the composition of the films become equal after the oxidation. The composition after the oxidation corresponds to stoichiometric bismuth telluride, while lattice parameters were not affected by the oxidative treatment, except the case of very high initial bismuth content. The morphology of the electrodeposits was controlled by parameters of the electrodeposition. First, the duty cycle, which is the ratio of the cathodic and the anodic steps duration in the potential control waveform. The particle size generally increases with duty cycle, results in rough, non-uniform films at too high duty cycle. As for the pulse frequency, high values of pulse frequency lead to the formation of large crystallized and dendrites. In order to facilitate nucleation on bare substrate, the electrode has to be pre-polarized at the potential more negative than that used for film deposition. We used pretreatment at -400 mV for 30 seconds to provide uniform coverage of the stainless steel electrode surface. Longer pretreatment leads to the formation of large crystals. To avoid non-uniform electrodeposition, also the solution has to be stirred and the surface active substance has to be added 60 minutes after the beginning of the electrodeposition. The time of the addition is important, as surface active substance prevents nucleation if added at too early stage. Concluding my presentation, in this work we developed the electrochemical way of synthesis of layered superlattice structures with controllable composition composed of bismuth 2 tellurium-free layers and bismuth bilayers building blocks. Verified their structures by X-ray diffraction, X-ray photoelectron spectroscopy and high-resolution transmission electron microscopy, and optimized the deposition process to produce films with good morphology required for thermoelectric applications. Additionally, we found out that selective anodic oxidation of bismuth bilayers and removal from the superlattice is possible and results in expanded bismuth telluride structure, which is of interest for introduction of other elements. Thank you for your attention.